Okay, well, so hi everybody. So here's the YouTube link for this lecture in case you want to scroll back. Um, so, okay. So this is lecture 13. And we're going to switch gears a little bit here. But before we do that, I want to reflect on, what the big picture is in this course so far. Because this course, we actually cover a lot of different topics and it can seem kind of scattered. So what have we done so far? Well, basically, we've done three things. So we've talked about propositional logic, then we've talked about sets and functions, and finally, we've talked about number theory. And then we've talked about one more thing, which is induction in the last two lectures, which is a new proof technique. But really all of these things, like the main underlying theme, I think, is to learn how to write proofs. So we've learned what does a proof mean, how do you find a proof, how do you read a proof, how do you write a proof, and the main achievements of what we've done so far are really related to proofs. So I just want to take a moment to recognize these. So one thing that we did in this course so far, which is different from what you did in previous math courses probably, is that we actually built everything from scratch. We built everything from first principles. Right? So we started off with definitions. And then using those definitions and nothing else, we arrived at some pretty interesting theorems, including like Fermat's little theorem and things that are not at all obvious. And we did it completely from scratch. And this is really this is the point of proofs, that you can completely own the mathematics that you're creating. And maybe I should make that a separate point. We essentially learned we learned how to create mathematics. Like, people often ask me this, like, okay, you're a mathematician, so what do you actually do? Like, what does research actually mean? Well, it literally just means proving new theorems. And this is the process by which you prove new theorems. And then, yeah, we learned the mechanics of how to read and write proofs. So this is, and of course we learned about number theory, and we learned some content. So what we're going to do now is we're going to do two topics. One is counting, which we're going to do for the next couple of lectures. And the other is probability, which is one of the most useful things you learn in this course, which is how to reason rigorously about uncertainty. And in this section of the course, there's more emphasis on content rather than structure. So there's less emphasis on writing. On writing proofs, although there is a very high emphasis on precision, which on being precise with definitions and quantifiers. But still need to, I don't know, write precisely. And after that, we'll go back to writing sort of long proofs. But really, in this part of the course, we'll be writing about things that are maybe a bit more general than what we wrote about earlier, which were numbers and sets. Okay, so what's today's lecture about? So it's going to be about counting, and there are essentially three parts of the lecture. So one is the basic rules of counting, which are in the book called the product rule and the sum rule. And then that's going to be the bulk of the lecture. And then we're going to discuss a few other counting techniques, which the book calls the subtraction and division rules. And I should say that the content of what we're doing today is in sections 6.1 and 6.3, which is a little bit different from what's written on the schedule. 6.2 is about the pigeonhole principle, which is, I think, actually conceptually quite different from this. So I don't know why the book does that in between. We're going to do that next time. Okay, so let's start with counting. So what is counting? What do I mean by counting? Okay, so the goal in counting is to count the number of objects with some specified property. So what do I mean by that? Well, okay, here are a few examples, and we'll end up considering all of them. So example one is count the number of bit strings of length 10. Okay, so what is that? That's literally, it's a set of objects. It's a set of all sequences, or let's use a letter B. It's a set of all sequences of 10 numbers, so that each of these numbers is either 0 or 1. This is a formal way to write bit strings of length 10, but they're really both unambiguous descriptions of the same collection of objects. Here's another example. How about something a little more complicated? Let's count the number of bit strings of length 5 ending in 2 zeros or beginning with 1. Okay, so it's a sequence of 5 zeros or 1s, and I wanted it has to satisfy these properties, either ending in 2 zeros or beginning with, sorry, there should be an N here, beginning with 1. Or I don't know. I guess there's a lot of news about rankings these days. What about what is the number of different rankings of the set Cal, Stanford, UCLA, and USC? That's a collection of objects. Or maybe we're interested in gambling. What's the number of ways to what's the number of ways to draw 2 cards from a deck of 52 cards? So ordered pairs of 2 cards from a deck of 52. So the 2 cards in this case, to be totally explicit, I should specify the 2 cards have to be different. So if you're playing blackjack, you don't get to draw the same card twice. So we'll be very precise about things like this. So here, distinct cards. Or maybe, I'm interested in poker, and then I'm interested in the number of possible hands I can draw in poker. So here I'm interested in poker hands. So a poker hand is an unordered set of 5 cards, right? So an unordered set of 5 cards from a deck of 52, right? Because in this, I suppose in poker, if I draw 5 cards, I don't care about the order of the cards. So these are all different types of objects. And these are examples of counting problems. And in terms of what we've learned about sets and functions, a counting problem is logically equivalent to just a question of finding the cardinality of a set, right? So it's equivalent to saying find the cardinality of some set S, which is given as all objects X such that X has some property. And that's not obvious, right? Because I'm not listing the set S explicitly. I'm just implicitly telling you what it is in terms of some property. So in this class, we're going to learn techniques, or in this lecture, how to solve all of these problems and more. But any questions so far? I should say unordered sets. Yeah. Okay. So let's start with simplest. Let's start with example number 1. So I guess I'll just copy paste this. Okay. I guess I'm missing a parentheses here. Okay, so how would you count the set of bit strings? Well, okay, so the naive way to count anything is just list all of them. Okay, so come up with some system of listing them. So maybe this is one of them, and then we just increase them. And then maybe we add 1 each time. And we keep doing this forever, and then we count them. Okay, that's not a very efficient, that's not the point, right? You could always do that. But yeah, so this is not what we mean, right? This is kind of trivial.
Can you say how many numbers are represented by 10 digits of binary number?
That's an interesting thought. So you could say how many different numbers. So here's an idea. Consider how many numbers are represented by binary expansions of length 10.
Up to 10.
Up to 10. Okay, up to 10. So that's an interesting idea. So I think what you're essentially trying to say is that you know, there's a bijection between this set and some set of integers. That's kind of what you're proposing, right? So this is saying that you're trying to find a bijection F from this set to some other set A, where A is a set of integers. That's an interesting thought. That can actually, yeah, that will ultimately work, actually. So we'll come back to this idea of bijections later. For now, let me tell you an even easier way, which doesn't require knowing anything other than what a bit string is. Okay, so here's another way. So here's maybe a better way than the naive way. So the thing is that this is a set of objects. And what I'm going to do is I'm going to ask, how do I construct an object in this set? Okay. What choices do I need to make to uniquely specify an object in the set? So I'm going from just the set to asking, what is a process that can generate elements in this set?
So for each of the 10 digits of the string, you have two choices.
Yeah, exactly. So observe that every element of this set, let's call it B underline in S, is uniquely specified by a sequence of 10 choices. Right. So what are the choices? So let me just write them down. So C1, the first choice, I'm going to use C1, C2 to indicate the choices, is choose B1, the first digit, which has to be in 0 or 1. Okay. And now C2, the second choice. So I haven't constructed a string yet. I've just chosen the first bit. The second choice is, given the first bit, choose the second bit. And then the third choice is given the first two bits, choose the third bit. And then if I do this 10 times, I have these 10 choices. I have uniquely specified a string. So what that uniquely specified means, after I make the choices, there's only one string. And for a given string, there's only one way to make the choices. Okay, so what I've done is I've turned this counting question into analyzing the sequence of 10 choices, which is actually a process, right? For constructing an element of the set. So now the the upshot of this is that I've broken down this complicated task of choosing an element of this big set into a bunch of small tasks of making these little choices of one bit at a time. And for each of these little choices, it's very easy to count the number of ways to make that choice. So how many ways are there to make the first choice? 2. How many ways are there to make the second choice?
2.
4.
Also 2.
2. So this is the key. So somebody said 4, and this is a point of confusion. C2 is just a little choice about the second bit. It's not the whole string. So you're given the first bit, and regardless of what the first bit was, there are only 2 ways to choose the second. Now, what about the third bit?
2.
2, right? And so on for all of them, right? So there are 2 ways of making each of the little choices, given the previous choices. And so the total number of ways to make all of the choices, C1, C2, all the way up to C10, is the product of the number of ways to make each of the choices. So in that case, that's 2 times 2 times 2, 10 times, which is 2 to the 10, which is 2 to the, which is 1024, I suppose. Okay, so let me, in order, sometimes it helps to visualize this. So there's a visualization sort of tool that is used in the book called a tree diagram, which we will not use for doing formal mathematics, but it's helpful to visualize, is that you can organize the choices in a tree. So at the beginning, you have the root where you have no choice has been made yet. And then the vertical dimension of the tree corresponds to the choices that you're making one by one. So the first layer corresponds to the choice C1. And there are two branches for this choice, right? You can either choose 0 or 1. And then after you've made C1, for each of those ways that you could have made C1, you have two ways of making C2, which are again 0 and 1. And then now for each of those possible ways of making C1 and C2, you have two ways of making C3. And then at the bottom of the tree, after you've made C10, you have the leaves of the tree. So leaves are, okay, so let's introduce some terminology, which we'll use more later. So these circles are called nodes. And a node without any branches going down is called a leaf. Okay. And so really what my way of thinking is doing is it's saying, hey, the set I wanted to count is in one-to-one correspondence with the leaves of this tree. And the way I'm counting it is by counting the number of paths down the tree from the root. That's the content of what I'm saying. Now, this example is maybe too simple, so it just seems kind of like I'm overthinking things. But any questions about this example?
Is the root also a node or is it not?
Sure, we can call the root a node as well. So root and leaf are special types of nodes. And then the key point is that the leaves are in one-to-one correspondence, namely bijection with S. And what we're doing is we're counting the number of paths from the root to the leaves, and that's equal to the size of the set. So the high-level idea here in this method is we decompose a big choice into a bunch of little choices, right? So the idea here is we decomposed a big choice into many little choices. Okay, so any questions about this example?
Also,
Yes,
question. Go ahead.
Can you go back to where you were saying at like C1, that means there's two choices, and at C2, there's four choices. Can you explain that more?
No. At C2, there are two choices. So C2 is the choice of the second bit.
Okay.
So there are actually only two choices. So this is a very important point. The number of ways to choose the second bit given the first bit is only 2. It's not 4.
Can you go back down to the tree?
Yep. So really C2 is asking if I'm at a node at, the, I guess, second highest layer of the tree, then how many downward branches do I have? So maybe I should say that. So the ways of making a choice are downward branches from a node. Okay, let me now do another maybe more interesting example. I'm actually going to do example 4 now, actually. So number of ordered pairs of 2 distinct cards from a deck of 52 cards. Okay. Now this is a big choice, right? Ordered pair of 2 cards. How do I do it? I want to break it into little choices. So step 1 is to identify a process, namely a sequence of choices for uniquely producing elements of this set. Or specifying that an object with a desired property. I haven't defined a set. Okay. So remember, this is a process now. So suppose I want to choose 2 cards from a deck of 52 cards. What's a process for choosing those 2 cards?
Pick the first card, then pick a second card.
Okay. So the process has 2 steps. C1 is choose the first card. And then the second choice is given the first card, choose the second card. And okay, really this is 2 distinct cards. If I draw a card from a deck, I don't get to put it back. So first step is identify a sequence of choices. Okay, good, I did that. Step 2 is find the number of ways for each choice. So, okay, let me just add a column here since that'll look nicer. So these are my 2 choices. Let me now add a column saying number of ways to make those choices. So how many ways are there to choose the first card?
52.
52.
52, yeah, just choose any card, right? So 52. So again, visualizing this in terms of my tree, what this is saying is I'm at the root. My first choice, there are many ways, there are 52 ways to make C1. And now I'm at one of these nodes where I've made one choice. So this is the tree diagram. Okay, but now the interesting thing is how many ways are there to choose the second card given the first card?
51.
51, because I already chose the first card, right? So this is the interesting thing, that this tree is different from the tree in the bit string example, because at the second layer, the number of branches going down is 51. So this is 51. And this process uniquely specifies an ordered pair of cards. Really what we're doing under the hood is we're saying, these sequences of choices are in bijection with the set itself. So then step 3 is just, well, the total number of choices is there for the product. Total number of pairs equals the total number of choices, which is 52 times 51. Okay. So any questions about this example? So why wasn't it 52 squared?
Because that also counts like when you pick the same card like twice.
Exactly. So this is an important feature in counting problems. You must always be aware when you're picking sequences of elements, are they distinct or not? And that affects what this sequence of choices, this process for specifying the object is going to look like. So, okay, so this is a general rule of counting, which is in the book called the product rule. So I'm going to summarize the rules at the end. So let me just write it here. So here's the product rule. Here's what it says. It says, let's see, how do I want to phrase it? Yeah, so suppose an object can be uniquely, so an object with the desired property can be uniquely specified by a sequence of n choices, C1, C2, all the way up to Cn. And the number of ways to make the first choice is n1, and then for all ways of making the previous choices, for all ways of making C1, the number of ways to make C2 is n2, and then for all ways of making the previous choices, C1 and C2, the number of ways of making C3 is n3, and so on. Okay, maybe n is not a good letter. Let's use k, since n I'm already using n, and so on up. So for all possible ways of making the previous choices, is equal to nk. Then the total number of objects is just the product. So you multiply all these ways of making the little choices together. So this is called the product rule, and it has a picture associated with it. The picture is you have a tree, and the key feature is that all the nodes at a level have the same number of children. Right? So the first layer corresponds to C1, the second corresponds to C2, the third corresponds to C3. But the number of children at a layer doesn't depend on which node you're at. They all have the same number. That's the key property. So this is the tree diagram. So that's the product rule. So any questions about the statement of the product rule?
How would you prove this for k equals 2?
If you wanted to formally prove this, what this is really saying is that there's a bijection between the leaves of the tree and the number of paths from the root to a leaf.
Cool. Thank
Because
you.
then the number of paths you can I guess you can prove by induction is just the product of these numbers.
Awesome. Thank you.
I didn't want to do it formally since it's not very deep, but if you wanted to do it formally, what this rule is really emphasizing is that you're turning just counting the leaves into counting the paths. And the paths correspond to this process. And there's a way to break that down level by level.
Awesome.
So the product rule corresponds to a vertical decomposition of this tree. That's one way of thinking about it. Okay. And then more generally, given the product rule, how do you solve a counting problem? So general method to solve a counting problem. To solve, so to count something, there are actually 3 steps. Step 1 is to turn it into a process, right? So find a sequence of choices, C1 through CK, uniquely specifying an object with the desired property. Step 2 is count the number of ways to make each small choice. Assuming that this number of ways doesn't depend on the previous choices. To make each CI, given the previous choices. And then finally combine these using the product rule. Okay, so we're now going to follow this to do some more interesting problems. And maybe before I
Could you move back for a bit?
You mean to the end? You can just look at it on the YouTube link. So good. So okay. So there's one more rule. Or actually, let's just do one more example before moving on from this. Let's do the example of how many rankings of these 4 universities are there. Okay, so let's solve this using our method. So step 1 is to find a process. So choice 1 is choose the number 1 position. Choice 2 is choose the number 2 position given the first one. And then choice 3 is to choose number 3 given the previous ones. And then choice 4 is to choose the last one, right? Step 2 is identify the number of ways. So let's make a column for that. Step 2 is to find the number of ways. So the number of ways to choose the first one, there are 4 ways. Number of ways to choose the second one, well, there's 1 less because you already chose the first one. So ranking again, the implicit thing here is that in a ranking, nobody appears twice, right? So there are no repetitions in a ranking. So the number of ways to choose the second one is 3, number of ways to choose the third one is 2, last one is 1. And so step 3 is that the total number of rankings is just 4 times 3 times 2 times 1, otherwise known as 4 factorial, which is just 24. And this comes up so often that this has a name. So here's a definition. So an ordering of n distinct elements or distinct objects, let's say, is called a permutation. And the above example shows, I mean, the same proof works for any collection of n objects. So I guess this is a theorem, although this is so easy to prove. I don't know if we should call it a theorem. Or, well, yeah, okay. The number of permutations of n objects is n factorial. And distinct objects is n factorial. And the proof is what I just gave you. Any questions about this? Okay. So now I'm going to tell you another principle of counting, which is sometimes called the sum rule, but it's really kind of a triviality, but let's do it. So sum and subtraction rules. Okay, so the sum rule is the following trivial observation. It says that if you have two sets that are disjoint, so if A and B are finite sets, so let's assume, actually, let's say that. If A and B are finite and A is disjoint from B, then the cardinality of the union is just the sum of the cardinalities. Okay, so that's not rocket science. We knew that. Now, how does this come up in counting? So the key thing is this disjointness condition. So how is this applicable to counting? Well, let's look at an example. Let's go back to our list of examples. Let's look at example number 2. So bit strings of length 5. Actually, okay, that example is maybe a little too complicated for this. So let me do something. Yeah, let me just make a new example. Let's call it example 6. So the example is, suppose I want to count the number of yeah, 2-digit numbers with no zeros, such that both digits are even or both are odd.
Professor, can you scroll up just a little bit?
Sure.
Thank you.
Okay, so this is a well-specified problem. 2-digit numbers, none of the digits are 0, and both have to be even or both have to be odd. So let's call this set S. Okay, so formally it's a set of, pairs of numbers, right? So S, it's a set of pairs of numbers. Let's call them A, B, such that each of these are in 0 is not allowed, are in 1 through 9. And both are even or both are odd. Okay, and the order matters, right? So always be general principle of counting, always ask yourself, is the order important? And are repetitions allowed? So repetitions are allowed here. Well, okay, so observe that, you know, there's no, if you try to find a bunch of choices to generate an object from the set, you're going to run into trouble because suppose you choose the first number. Okay, so maybe before we start, observe that, so how many even numbers are there in the set? 2, 4, 6, 8 are even. And the rest of the numbers, 1, 3, 5, 7, 9 are odd. So there are actually more odd numbers than even numbers. So if you try to do this with just the product rule, you're going to fail. Because after you choose your first number, the number of choices for the second number is going to depend on your first number. It could be either 5 or 4 if your first number was odd or even. So product rule is not going to work here. So then you do this simple thing that S is equal to A union B, where A is, okay, you know, is just the ones with even numbers, right? So I don't know, A, B, and S, such that both are even. B is a set of pairs, such that both are odd. And now, okay, so now the cardinality of S is the cardinality of A plus the cardinality of B. And now you solve each of these problems separately. So let's solve cardinality of A separately. So can choose. Right. So how do you choose a 2-digit number where both are even? Well,
From that,
mhm.
pick from that first set once, then pick from it again.
Yeah. So for A, C1 is choose you know, A from this, not from the set A, from the set of even numbers. So choose A even. And C2 is, again, just choose B even. We're allowed to repeat. So then the cardinality of A is just 4 squared, which is 16. And then for B, again, you do the same stuff. You get that the cardinality of B is 5 squared, which is 25. So the total number of such numbers is 16 plus 25, which is 41. Okay, so in terms of the tree diagram, what happened here is very different from the product rule. Let me just draw the tree. So before I draw the tree diagram, any questions about this?
It's squared because you can have the same digit twice, right?
Exactly, yeah. If you
Okay.
weren't allowed to have the same digit twice, it would be like 5 times 4 and 4 times 3. But I haven't said anything about repetitions here. So implicitly, I'm saying repetitions are allowed. And the order matters, right? Because the numbers change if you swap the order. Okay, so the tree, it's instructive to look at the tree diagram here. Tree diagram is, okay, there are no choices. But now really what I did is I split this into 2 choices, namely, am I in A or am I in B? Are they even or are they odd? And then each of these had their own little tree diagram, which was different. In the even case, you had a branching factor of 4. Whereas in the odd case, you had 5. That's why you need the sum rule. You couldn't just use the product rule here. So any questions about this? Okay, and there's, let me just record this in our summary at the end. So sum rule. Actually, I'm going to record a generalization of the sum rule. So this is the sum. Well, okay, let me just write the sum rule. If A and B are disjoint, then the cardinality of A union B is just the sum of the cardinalities. And this corresponds to a horizontal decomposition of the tree diagram. Right? This is different from this vertical decomposition from the product rule. This is not splitting the big choice into small choices. It's splitting the number of ways to make a single choice into two subsets. Right? So this is a horizontal decomposition of choices in the tree diagram. So it's very different conceptually. This is a vertical decomposition of a big choice into small choice. Okay, so that's the sum rule. And then there's something which is a minor generalization of the sum rule, which is called the subtraction rule, because you end up subtracting some numbers. And this is just saying if A and B are finite, and now they're not disjoint, then it's this identity, which I believe you know already. The cardinality of A union B is the cardinality of A plus the cardinality of B. Sorry. Minus the intersection. Cardinality of the intersection. Let me move this. So this has, this Venn diagram associated with it that you've all seen. You end up double counting the stuff in here. So let's see how to apply the subtraction rule. To do example number, I think 2. Bit strings of length 5 ending in either 0 or beginning with 1. Okay. So, okay, we follow the 3-step process. So step 1 is to identify, a process, a sequence of choices. So step 1. Well, okay. So right now, actually, there's going to be a bifurcation in the process. So first, I'm going to break down this process into break down the set. So let's call this set S. I'm going to write S as A union B, where A is bit strings of length 5. Ending in 00. B is 5-bit strings beginning with 1. And the difference here between this and the last example is that these are not disjoint, right? In the previous example, you can't have a number where the digits are both even and both odd, right? So maybe the key point was that these sets were disjoint. In this case, it's not the case. The intersection is 5-bit strings that have both properties, right? Okay, so now, so according to the, I guess, subtraction rule, the cardinality of S, I can break it down into the cardinalities of 3 sets that are simpler, that don't have this OR. So cardinality of S is equal to cardinality of A plus cardinality of B minus cardinality of the difference of the intersection. And now I have to compute all 3 of these things separately. So let's do that. So let's do A, B, and A intersection B. So let me draw a picture. A consists of strings that, what is it? End in 0, 0. So it's strings that look like B1, B2, B3, 0, 0. So how many ways are there to choose to construct a string like that?
The third,
Excuse me?
2 to the third.
2 to the 3,
Because-
because the 3 choices are choose B1, choose B2, choose B3, and you're allowed to repeat and so on. So cardinality of A is 2 to the 3. B is strings that look like this. B1, or sorry, 1 times B2, B3, B4, B5. So there's no choice with 1, but you can choose the other 4. So the cardinality of B is 2 to the 4. And A intersect B is strings that look like this. Or sorry, so 1, B2, B3, 0, 0. And there are only 2 choices here. So cardinality of A intersect B is just 2 squared. And so the conclusion is that the cardinality of S is 8 plus 16 minus 4, which is 20. So there are 20 such strings. So this is not anything very complicated, but you have to do it precisely and carefully. The tricky thing in these problems, I mean, some general remarks, which I'll add to the summary here. So this is the, I guess, the subtraction rule, which I think is kind of a silly name, but okay. So a general principle here is always be aware of, are the objects you're counting ordered or unordered? And do you care about repetitions or not? So always ask, are objects ordered or unordered? And is repetition allowed? Because that's going to change the number of choices. Okay, so that's the subtraction rule. So any questions about that?
So like for most of the time we're using subtraction rule is because the question doesn't allow repetition.
Well, no. So this so repetitions versus no repetitions is more like, you know,
Because
in this
I
example
see,
with the 2 cards, I had 52 times 51, right? Not 52 times 52, because I can't repeat the same card twice.
because like the reason why I ask this because I saw the subtraction rule is the number of A plus number of B minus the intersection. So the most of the intersection that happen is the repetition, according to the Venn
No,
diagram.
so repetition here is being used in 2 different ways. So, yeah, okay. By repetition, I mean, if you're in all the problems so far, you're counting some kind of sequences or strings. And what I mean is, are you allowed to repeat letters or digits or elements in that sequence? I don't mean, so yeah, is repetition of symbols allowed of symbols, cards, digits, whatever it is you're counting.
Got it.
Great question. Okay, so now I'm going to move on to the one example we haven't yet covered, which is this unordered sets of 5 cards. So this is interesting, and this will bring us to the division rule. So let me make a new section here. Okay, so the motivating problem here is number 5. And the new twist here is we don't care about the order. Okay, so to solve this problem, I'm actually gonna do something that's not entirely obvious. So the difficulty with unordered sets is it's generally hard to find a process that uniquely generates an unordered set. Because inherently, when you have a process, there's an order in which you make the choices. Then it's kind of hard to throw that order away at the end. So what I'm going to do is I'm going to consider a related problem. I'm going to call that example 5 prime, I suppose. Which is a related problem, which is how now I want to count ordered sets of 5 cards from a deck of 52. And again, here the assumption is, there's no you're not allowed to repeat cards, right? So 5 distinct cards. So this is a different problem. But let's solve this easier problem. Well, this we kind of already know how to solve, right? So the solution to this example 5 prime problem is, well, okay, here are the choices. Choice 1 is choose the first card. Choice 2 is choose the second. Given the first, ... all the way up to C5 is choose the 5th card. Given the previous. So this is my process. And now the number of ways, okay, there are 52 ways to choose the first one, 51 ways to choose the second one, 50, then 49, and then finally 48. These are the number of ways. Because they're distinct, right? Repetitions are not allowed. And so by the product rule, the number of ordered sets of 5 cards is the product of all these numbers, which I'm going to write it in a clever way. It's 52 factorial divided by 47 factorial. Why is that? Well, because all the numbers up to 47 get canceled, right? So this is 52 times 51 times 50 times 49 times 48. So whatever, it's a huge number, right? I'm not going to try to calculate it. It's a very big number, but this is what it is. So this is a part of a general remark. State a definition. A sequence of R elements, R distinct elements, or R distinct objects, let's say, of R distinct objects. Is called an R permutation. These definitions are all in the book. They're not very deep definitions. They're just terminology. And okay, the number of R permutations of n objects. So the key now is that R might be different from n, right? Is n factorial over n minus R factorial by the argument we just did. So in the example above, what are n and R?
N is the number of cards in the deck. R is the number of cards we don't choose. Or sorry, R is the number of cards we do choose.
Exactly. So the number of ways of choosing R or R distinct objects. So this is an ordered sequence. The word sequence already means ordered, but I'm just emphasizing it here. Okay, so good. But we didn't solve example 5, right? We're interested in unordered. So how do we do that? So there's a sneaky trick you can do. Well, the number of ordered sequences of 5 cards is actually equal to the number of unordered 5 sequences or I guess sequences is not a good word of 5 okay, let's say unordered 5 cards times the number of ways to order a given set of 5 cards. Why is that?
We can like imagine constructing the ordered set from like the unordered perspective. So we figure out we can create all these different ways to draw the unordered cards. And then for each unordered way, our next step, our next choice in the procedure is the different ways we can order them.
Yeah, that's a
Or
great
how do we
answer.
order.
It's really just the product rule, right? So the reason is that you can construct, can uniquely specify an ordered, okay, let's use the word hands here. An ordered hand of 5 cards, unordered hand of 5 cards. Can you use an ordered 5 hand as follows? You have 2 choices. Choice 1 is choose an unordered hand of 5 cards. We don't know how to do that, but there is some finite way to do that. And the second way is order them. And the nice thing is, how many orderings are there of 5 cards?
It's 5 factorial.
Yeah, we just discovered that, right? That's just permutations. An ordering of n distinct objects called permutations, it's always n factorial. So they're always 5 factorial, so we can apply the product rule. So regardless of which 5 cards we're interested in, they're always 5 factorial such orderings. So that means we can apply the product rule. So I need to insert a page here because I've run out of space. And so this follows by the product rule. So now I have the answer, right? So what's the number of unordered sets of 5 cards? Now I can just use the word sets. Is the number of ordered sequences of 5 cards divided by 5 factorial. So in this case, it is, we already calculated that, that's 52 factorial divided by 47 factorial times 5 factorial. So it's some huge number, but we exactly calculated it. And there's a picture associated with this. Let me write down the picture. The picture is, let's say here you have ordered sequences of 5 cards. So here you have like 1, 2, 3, 4, 5, and then 1, 3, 2, 4, 5, and then I don't know, 3, 1, 2, 5, 4. You have a bunch of such things, right? You have all possible orderings of this particular choice. You have 5 factorial orderings. But now when you, if you throw away the ordered and you look at unordered sets, then there's only 1. 1, 2, 3, 4, 5. And all of these guys get mapped to this one unordered set. But the beauty is that the number of things that get mapped to one unordered set is always 5 factorial. That's why you can just divide it out. You can count the ones on the left. And then because everybody on the right gets counted 5 factorial times, you can just divide out by 5 factorial. So this is maybe the most subtle thing we've discussed today. So let's pause and just consider this. And please ask any questions if you have.
So can I interpret it as like division rule is just a product rule, like divided by the order, like how many orders of like each of the 5 elements can be can form. So it's just divide all the order pairs.
Yeah, I mean, I'll formally state the division rule in a moment. But yeah, that's right. That if you count, you know, there's a relation between counting ordered sequences and counting unordered sets. And the relation is you count every unordered set exactly n factorial times if it has n elements. And so if all the sets are of the same size, you can just divide by n factorial. That's how we got this sneaky trick. So let me just state a general fact. So here's a definition. This is a terminology that's used. So an unordered set of R objects from a collection of n objects is called an R combination. And the number of them, the number of R combinations of an n element set is denoted C n comma R. It's n factorial. So okay, it's the number. Oh yeah, I should have developed some notation. So it's the number of permutations. So let's give that a name. The number of permutations is denoted P n comma R. an ordered sequence of r distinct object chosen from n objects. Yeah. Is this number. Make a little more space for this. So Pn comma r is equal to this. Okay, so the key point is this. And now the number of combinations has a different name, CNR. That's just PNR divided by r factorial, which happens to be n factorial over n minus r factorial times r factorial. And that what our little example here is a special case of this formula. So in the above example, n is 52 and r is again 5. The difference is we don't care about the order, so obviously there will be fewer unordered objects, and it's exactly what you'd get if you divide by r factorial. So okay, any questions before I explicitly state what the division rule is? Okay, let me just state the division rule now then. So let me state it at the end of the summary. So I'm going to state it in terms of functions and sets. So here's the division rule. Oh, did I add too many pages? Okay, yeah. Okay. So here's what it says. It says that if f is a function from a to b, which is m to 1, what that means is that for every element in the codomain, the inverse image of the set containing that element has m elements. So the picture associated with this is this picture that you saw in our example with the unordered hands of poker playing cards. What this is asking is that there are always, for every element in the domain, I mean, okay, this picture is not very good. There are exactly m elements for every element of the codomain, there are exactly m elements of the domain which map to it. Okay, that's not a good picture either. Then the cardinality of A and cardinality of B are related. Then the cardinality of B is equal to the cardinality of A divided by A. So how does this apply to the above example? So in the cards example, A is the set of all ordered sequences, A1, A2, all the way up to A5, such that, let's say, AI is a card. So let's just say AI is a number between 1 and 52. And B is the set of all subsets, A1, A2, A5, such that these things are numbers between 1 and 52. Notice the difference. One is ordered, one is unordered. And the function f here takes a sequence and forgets the order. So this might take a little while to chew on, but this is an abstract way of saying why you get to divide by 5 factorial, because every unordered set comes from exactly 5 factorial ordered sequences. So that's the division rule. And that's how we solve these problems with unordered number of cards. So that's it. Any last questions?
May I see the very end of the part?
Sure.